Okay, I think it's time to start our keynote session 3 of WPW 2021. Welcome everyone to day 1, session 3 of our conference. It is a great privilege for me to introduce our third keynote speaker, Burak Ozpenci. Burak is the section head of Vehicle and Mobility Systems Research Section at Oak Ridge National Lab. Burak has his bachelor's degree in electrical engineering from Orta Doğu Technical University in Turkey, better known as METU or Middle East Technical University. And he received his master's and PhD degrees from the University of Tennessee in Knoxville. Burak has served in a variety of capacities at Oak Ridge, as well as serves as a joint faculty at the University of Tennessee. Burak is a fellow of the IEEE and has won numerous awards. It is a great privilege to have him here talk about wireless charging for electrified roadways. Burak, with that, please take it away.
Thank you, Ram. Let me share my screen. By the way, in that photo, I look really young. I don't know how old that photo is, but let me do this. All right, can you see my screen now?
Yes.
All right, perfect. Let's move it to slideshow. There we go. All right, good morning, good afternoon, good evening, wherever you are listening to this. Thank you for calling in. So today, my name is Burak Ozpenci from Oak Ridge National Laboratory, and today I'm going to talk about wireless charging for electrified roadways. But before I start, I want to say a few things about Oak Ridge National Laboratory. That's where I work. And here's a photo on the left side. You'll see this is our main campus. It's like a university campus, but our focus is more than education, it's more research. And we have a lot of different disciplines we're working on this campus. But a couple of things I want to highlight. Every few years, we have the fastest supercomputer, and I think next year we're going to get another one. And last few years also, the lab also contributed to the addition to the periodic table called Tennessee, which are not really related to what I work on, but these are cool things to know about where I work at. So we are one of the 17 Department of Energy, US Department of Energy national laboratories, and we do a lot of transportation work too. Transportation work is usually done off campus. We have another building where we focus on everything from engines, fuels to power electronics, motors to all kinds of electrified transportation, simulation modeling, and anything you can think of in transportation under one building. So we're really excited about that. And we have been working on wireless charging although too. We started in 2008 with these bulky coils you see, perpendicular coils, and they were real large. Of course, we just want to demonstrate 1 kilowatt, and over the years we demonstrated 120 kilowatts, and we're working on a few other projects I'm going to talk about. So next few slides I'm going to talk about our recent accomplishments. After that, I'm going to talk about electric roadways and what I understand when we talk about electric roadways. Then I'm going to talk some about our dynamic wireless charging work we're working on right now. And I will end the presentation with what we're planning on doing in the future, hoping that we get the funding to do the work. So how is ORNL's wireless power transfer approach different than some of the others we've seen? We have high power wireless charging, but not necessarily the highest power. Our goal is to look at a wireless charging system as a single line power flow. So we don't want to parallel multiple systems. Our goal is what can we achieve with a single line power flow, that you can use as a module if you want to put multiples of these in parallel and get higher power levels. So in that case, for example, our 120 kilowatt wireless charging system, you add 8 of them, you're at 960 kilowatts, almost at a megawatt. So that was the latest demonstration we had a few years back. Of course, we're going forward we're working towards a higher power wireless charging. With that, if we get a 300 kilowatt system, then you can parallel those things to get higher power levels too. So we're trying to get the maximum power we can get with a single line power flow. So last February, actually, just before the COVID started, we had our last demonstration. That was a bidirectional wireless charging demonstration. This is a project we work with UPS. The challenge with this work was that we had to have an 11-inch gap as opposed to a 6-inch gap we used to have before. So that's much larger than what we were comfortable with before. But this was a good challenge for us. And the other aspect of this project was that we had bidirectional, we did a bidirectional system. So the goal was to charge the truck at 20 kilowatts and send power back at 6.6 kilowatts through an 11-inch gap with a higher than 85% efficiency. When we did the demonstration, we delivered more than 20 kilowatts power at 93% efficiency to the vehicle, and in reverse, we delivered 12.8 kilowatts back to the grid at 89.1% efficiency. So this project is still going on, where we are ready to ship this vehicle to a UPS campus where more testing can be done, long-term testing more or less. And the PI, you will hear two names in these presentations because a lot of these projects are led by my R&R colleagues. So this one and the next one I'm going to talk about are led by Dr. Omer. So the second one, second update on our projects, we have been working on wireless extreme fast chargers for a few years now. The definition of extreme fast charging is anything higher than 350 kilowatts. So we are trying to get to that power level, but with the vehicles we could get right now, we're looking at 100 kilowatt wireless charging with a Hyundai Kona electric vehicle, which is already in our laboratory, and we're working on retrofitting that. And the Porsche Taycan is on the way. With Porsche Taycan, we will be getting up to 300 kilowatts of stationary wireless charging, wireless power transfer. Now, another important point of this project is, in this case, we're using polyphase coils we developed in the lab. And with these, we can achieve really higher surface power densities. So the way, Dr. Onar, his example is the ground coil looks like a extra large pizza, and the 100 kilowatt coupler for under the vehicle is like a small pizza, and the 300 kilowatt is like a medium level pizza. And we have published a lot of papers in these things, so you might see the actual dimensions of those in some of these presentations. So talking about E-roads or ERS. So electrified roadways is one way of calling them, E-roads. And the other one is electric road systems, so ERS. And I see ERS mostly in Europe. We have been using E-roads here, but of course, it's not like necessarily geographically separated. I mean, we both can be used for these applications, at least the way I see it. And when you look at these things, it's not just a wireless charging, inductive or capacitive, but there's also work going on in overhead conductive catenary systems. So some you probably have seen them, especially in Europe, in various locations where they have in historic downtown areas. But as you see here, sometimes these are now being demonstrated for trucks or buses. So you can have electrified roadways or electric road systems where you're powering these vehicles at all times. So the second one, side rail conductive, is an interesting one because that actually helped us get into wireless charging work. So in 2007 or 8, there were workshops being conducted about this technology where you have a vehicle running on the highway and an arm separates itself from the vehicle and connects with the rail on the side of the road, like you see here, couples directly on the side of the road. So this way you can transfer power. So there's a paper here from Honda. You can see the SAE paper, and they have a study of 400 kilowatt system while using this technology. At that time, we decided to go with wireless charging. So this was, again, 2007, 2008, 13 years ago. So we've also seen some demonstrations in Europe of in-road conductive systems where you have actually conducting rails inside the road, in the road, and then you have some kind of a conductive connection with the rails. So as the vehicles are running on the road, they can connect to these rails and get powered. Of course, the focus of this presentation is dynamic wireless charging, but I think we should still keep an eye on what's happening. These are, I would say, not necessarily competition, but I think these are different technologies we have to keep an eye on and see what advancements are being made, and to maybe compare our technologies to what's going on around the world. So to achieve that, actually, last year we proposed a task under International Energy Agency. Actually has a program called Technology Collaboration Program for Hybrid Electric Vehicles. And under that, they have multiple international organization where multiple countries form different tasks. I led a task on wireless charging, which ended a couple of years ago. And now we started this one. Task 45 is on e-roads. So what this program does is brings people together from different countries, as you see lower here, people from Switzerland, Norway, Netherlands, Germany, and Sweden. They are already on board. So there are meetings going on, and with this task, there will be 2 get-together, 2 meetings, 2 workshops a year. So all these people get together and focus on different aspects of these technologies. So dynamic wireless charging is also a part of it, but it's not the only one. If you're interested in joining, or if you want to know more about that, I have the contact information of the operating agent who is leading this effort. And here's at the bottom is the website of the task. So since we talked about e-roads, I see all kinds of numbers. What kind of power levels do we need for these e-roads? For example, to power a sedan, an electric sedan. So I said, okay, let's look at some of the energy use numbers for these vehicles. So there is a very nice website, if you haven't seen before, www.fueleconomy.gov. If you're into buying a car, you can actually search for people reporting the mileage, not just electric vehicles, but hybrids or gasoline vehicles. And this lets you also compare different vehicles and their gas mileage, and also the savings you have, how much you're going to spend for electricity or gas, and all these things. So it's a very useful website, and actually Oak Ridge National Laboratory manages it too. So it's a good opportunity for me to show that actually this website really is helpful. So I have a few vehicles here. You see, the first one is the Chevy Bolt. It has 120 miles per gallon electric, but what I'm looking at here is the 28 kilowatt hour per 100 miles, and 27 for Tesla Model Y and Ford Mustang and the Volkswagen. You see different numbers here. So let's pick the Chevy Bolt, 28 kilowatt hours per 100 miles. So if you divide it, if you want to find the energy per mile, then you can divide by 100, then you get 280 watt hours. So if you assume the vehicle is running at 60 miles an hour, so that means this makes it easier. That's why I use 60 here. So the car passes through 1 mile in 1 minute. So now I'm assuming that the mile, we have a mile length of these dynamic wireless charging systems. So if you want to calculate the power, energy divided by time, so we have 280 watts. I'm replacing hour with 60 minutes, and it takes 1 minute to pass through. If you multiply these, you get 16.8 kilowatts per 100 kilowatt coverage. So, and if you look at different demonstrations of dynamic wireless charging, I've seen 20 kilowatts a lot being used, and that covers this. Now, we are looking at it differently. Now, let's say we don't want to have 100% coverage. Let's say we want to have 10% coverage. Can we do that? Yes, we can. The only thing we have to do, of course, is we have to bump up the power by 10 times. So in that case, we're looking at 168 kilowatts. So that would be the main difference. So, having a continuous wireless charging lane could be useful, but we also think that having a shorter electrified distance of the roads might have its benefits, and we've been focusing on that more. So dynamic wireless charging, as I mentioned, for the dynamic wireless charging work, the PI who leads the efforts is Dr. Veda Carey. When you look at range anxiety, that's one of the motivations we have. Electric vehicle owners, if you have an electric vehicle, in the US, at least, there are so many charging stations, but you still have this anxiety where if something goes wrong, and if you run out of charge, there might not be a charging station close by. You always have to worry about it. And with the new electric vehicles, you see the range is going beyond 200 miles, but still, I have a vehicle that supposedly has a range of 300 miles, and at times I have range anxiety. So this is still there. So if you have limited range, what do? We increase the battery capacity, and then what happens? Basically, you're increasing the weight of the vehicle and the cost of the vehicle, and you're reducing the energy efficiency of the vehicle. So in this sense, dynamic wireless charging can be a solution for range anxiety. So some of the assumptions for us, we're looking at a charged balanced mode. So basically, we are not trying to charge your vehicle from 0 to 100%. We are just trying to give you enough energy to cover the mile you passed. And we're looking at primary roadways. I'm going to talk about that a little later. For now, we're looking at one electrified lane instead of multiple lanes. So with that, you can actually have you need some kind of battery still when you're going off the dynamic wireless charging roads, but they can much smaller. So that will help with the weight and the cost. And again, we're using the single line power flow. So we're not paralleling anything at this point. Now, to complement this, I'm also thinking if you want to eliminate the range anxiety, it would help to have static wireless charging at home and at work. So we did a somewhat of a high level cost and feasibility study. We looked at the vehicle cost, increasing with the charging power level. We looked at the infrastructure cost. We looked at the roadway coverage we would need. We had some equations here and there. I'm not going to go into those details, but something I want to highlight here. We said, okay, if you have a vehicle that can accept extreme fast charging. So we picked the vehicle, we looked at the cost there, the cost parity at this line, if you follow it, that intersects with the vehicle cost line, and then we go down. This is the power level we said we want to go with. That is 235 kilowatts. So when you look at the roadway coverage, that corresponds to 8.2%. So this was our calculation. If you have different ways of different things you want to look at, different objectives, then your numbers might be different. But for our study, this is the number we picked. And we have this chart that really helps with deciding what kind of coverage is needed and what kind of power level is needed. So looking at the primary roadways I mentioned, in the US, there are 4.2 million total paved roadways, and 1.6% of those are primary roadways. And this is interesting too. You might be interested. Sorry? Okay. So the primary roadways, even though they are at 1.6% of all the paved roadways, 32.9% of the annual driven miles are on the primary roadways. That's why we've been focusing on them. So if you look at the 8.2% of this number here, we get 5,500 miles. So basically, if we can electrify 5,500 miles, then we can cover all the primary roadways with dynamic wireless charging. So for this work, we're looking at 10x the power level. Instead of 20, we're going to 200 kilowatts, and we're looking at 8 times the service power density too. So when you look at the cost components, of course, you have to think about everything. We have the grid connection, installation, road retrofitting. We learn a lot about civil engineering when you're doing that, power electricity materials on the road side or the grid side, but also vehicle power electronics and onboard battery. You're trying to include all of these things in your calculation. So with that in mind, this is what we come up with. So we have, as you see, renewables connected, we have the power lines, and we have a dedicated line of dynamic wireless charging that can be used. So on the infrastructure side, of course, we have all these different components. And on the vehicle side, we have the wireless power transfer system, power electronics, and the battery. So with that, if you look at 8.2%, then we're looking at, let's say you enter the mile right here with this state of charge. So there's no electrification at this point, basically no electrified roads at that point, because the electrified segment comes later. You're using the energy in the battery, and then you come to this strip over here for 128 meters, or a length of a soccer field, and you can start charging your vehicle. And then after that, you're using the battery again. So when you enter the mile and you exit the mile, it's exactly the same state of charge. That's the ultimate goal in this case. So we have been working on the hardware for this. Here you see the 200 kilowatt power electronics, the vehicle side power electronics developed for Hyundai Kona. For the dynamic wireless charging, we're going to use the Hyundai Kona as our vehicle. And this is the secondary with the rectifier and DC-DC converter. And here you see the primary side. So again, this is built, this is ready. It's ready for 200 plus kilowatt operation at 85 kilohertz. But our goal is to demonstrate when we actually have the real demonstration, we want to demonstrate at 200 kilowatts. We think that that should be sufficient for now. And we're looking at power electronics. We're using silicon carbide devices from Wolfspeed. We have been using them for a while, and the efficiency, we're getting really high efficiencies. And for this one, we're expecting close to 99% efficiency. So here's another look at what we have. Here's the roadside coil, and here's the vehicle side coil. And something else you have to think about when you look at dynamic wireless charging, because as I mentioned, we usually, when you look at the vehicle clearance, you're looking at around 6 inches. But now we have to bury these things in the pavement, and we have to think about how deep we have to bury them. So talking to the people who are involved in the pavement, they said we need to bury them 2 to 4 inches. So with that, all of a sudden we have a 10-inch gap instead of a 6-inch gap for a regular vehicle. And while we're looking at these, we're considering the pavement implications or infrastructure implications. We also bought a system recently. This is a new system that was just installed that can go up to 20 miles an hour with the coils we're developing. So we can actually demonstrate this first in the lab to see how this will work before we install it on a vehicle and actually go to the field. For the demonstration, we picked American Center for Mobility in Ypsilanti Township in Michigan. This is a very nice facility where they have multiple roads where you can do all kinds of testing. They do a lot of, from what I understand, they do a lot of autonomous vehicle testing too. And we want to install our dynamic wireless charging system over here and evaluate it. And they have been really helpful working with us. So we're looking at 4 200 kilowatt transmitters embedded over 25 feet. We're not going to do miles of these things, okay? We had to pick a certain distance for us to demonstrate this. After we do this, then we'll have more confidence so that we can actually go into the real world and install this in the real world. We're looking at power densities of greater than 400 kilowatts per meter square and efficiencies of greater than 90%. So this will be hopefully done in September. At least that's our goal. While we're working on this, we're also not ignoring the grid side work. Some of you might have seen this animation. I like it. That's why I show this. And one focus area we've had on the grid side is we don't want to use what's being used for stationary or static wireless power transfer systems and use them for dynamic wireless charging because they're not necessarily the best for grid connection and for power oscillations. We're designing our own system so we don't pollute the grid either. So we're designing our system. That's why we've been focusing on different aspects of these coils too. But on the other hand, looking at the, again, grid perspective, something you might or might not have thought of, but we're looking at different aspects of dynamic wireless charging, or actually this can apply to e-roads too, possibly. So we are actually from the grid side, we're distributing the load. So if we don't have this, if we don't have dynamic wireless charging, you will have to charge at home, or if you're traveling long distances, you might go to a charging station and charge at 300, 400 kilowatt charging stations, and that's quite a peak power demand. So if we have dynamic wireless charging, what you can do is you can charge at home, and you can charge on the way to work, and then you can charge at work. So basically, you're spreading the charging load in different locations. And actually, since you're never going to go to a lower state of charge in your vehicle, you're keeping the state of charge at a certain level, you really don't need auto power. So maybe you can have slow charging at home, and this way you can have maybe level 1, level 2 charging would be more than enough for you. So that's something lower level 2 basically would be good for you. That's something to think about. And if you think of long distance driving, not just even then, you're driving in an hour, you're going through 60 miles, and the demand you have from the grid again is spread along those 60 miles. And of course, you can have renewables and on-site storage to help with this too. So the last slide I have in my presentation, I just want to highlight this because this is something we're looking at now too. So medium and heavy duty vehicles, we're trying to work on electrifying them. And something interesting you might or might not know, 4% of the vehicle population, these vehicles occupy 4%. They had 4% of this. And they have 9% of all vehicle miles traveled. So they are much lower than the passenger vehicles or light duty vehicles, but they use 26% of the gallons of fuel. So they use out of fuels. Dynamic wireless charging could help with this too. But that brings another subject you have to think about. They need, from what I see online, they need 2 kilowatt hours per mile. So they might need a lot more energy. They will need a lot more energy than what we have for light duty or passenger vehicles. That's all I have. Thank you.
Thank you, Burak, for a wonderful talk. And I just want to remind the panelists, and I've also typed this in chat, you can post your questions in the Q&A panel that's on the bottom of your screens. And we will be asking questions from there. But just to get started with some questions, Burak, I have one. So you talked about 20 kilowatts as sort of the average power needed, or roughly that for sedan type of vehicles. But at the end, you also mentioned that these long haul and these big trucks and buses. So how do you envision what is going to need dynamic wireless charging first? Is it going to be the big trucks and buses? And in that case, what would be your sort of design in that case? Would it be higher power systems or just more percentage of the mile covered?
Very good question. Actually, this slide, we've been thinking about that now, right? Exact same thing you're thinking about, because we're working on these passenger vehicles or light duty vehicles, but now we're seeing there is a lot more need for these long haul heavy duty vehicles because you see how much energy they need. The problem with the electrifying these vehicles is they need, if you're going to use a battery, they will use a huge battery. So can we use dynamic wireless charging to help reduce the size of those batteries? And if we can achieve that, I think they might be the first ones to take this over because they get the efficiencies. And if you don't have to carry these large batteries, that would be a win-win. Another point of on these heavy-duty vehicles, if you're driving around and these vehicles roll around, sometimes they're going uphill, they're going slow, right? They're going much slower than the passenger vehicles. So two things you can think of. I think those hills are great applications of dynamic wireless charging for a couple of reasons, because these vehicles need a lot of energy going uphill, so we can provide them from the road. But also you have to think about, they go slow. So since they go slow, they will have enough time to get the energy they need compared to passenger vehicles.
Thank you, Burak. That's an excellent observation. So we have our first question in the panel. This is a question from Lei. He says, how would you achieve smooth dynamic transition as you're transitioning between the different coils? So you're obviously designing that correctly to get that nice smooth thing that you showed us, but how do you do it?
Exactly. So now we're going into all those details, with the controls of these coils. If you're asking for, if you're using ultra capacitors or something, we're not using any of those right now. But we have interest in, if we need them, we have interest in using them. For now, if you need more details, I will refer to some of we are publishing out of papers. I would recommend you looking into those in the control of these systems.
All right. Just to kind of ask the same question in a different way, are you also doing something special on your coil designs for these dynamic systems, or are you still using the kind of coil designs you showed us for the stationary systems?
No, we're not using the stationary systems. This is like, we're using double D coils in this case.
Okay. All right. Um, Again, please post your questions here. I am also monitoring the Hoover site, but I didn't see any questions there yet. So, and if you have a question that you don't have time to write, but you just want to ask, um, go ahead, raise your hands. I think we have a question on the Hoover site. So let me see if I can read it. So the question says, if you're retrofitting hybrid vehicles with wireless charging, um, could it help use those vehicles, or would it help have those vehicles use less gasoline? And what is the effort in converting such vehicles? Is there any effort
We're not
on
actually
hybrids?
looking at hybrid electric vehicles. And if I had to guess, if you use plug-in hybrid electric vehicles, with a decent sized battery, still maybe 50 miles or something, then of course you will help in reduction of the of gas consumption. For hybrid electric vehicles, I think this would be a lot more expensive for what's needed for this.
Right. Okay, we have one more question from Akshay Sarin. He says, any insights on generation demand imbalance on the grid side with large intermittent loads?
So we started looking into them. Actually, we have a paper recently. That one is assuming continuous dynamic wireless charging. Basically, if you have the whole mile covered, I would recommend you looking into that. We have to, we have the power there. There's so many different scenarios you can think of. Different vehicles needing different charging systems, charging requirements, charging demands. So you need to aggregate them and then look at in the aggregate. So I highly recommend looking at a paper by Rong Zhang. He recently published a paper. I think you can get more insights on this side.
Okay, we'll just take a couple more quick questions. So we have one from Rabail Namiri. He asks, can you talk about the leakage field values with the existing limits dictated by the standards?
Very good question. So we're looking at the IGNERP limits. So when we test our systems, we're evaluating. We have NARDA systems. We're measuring the fields all around as dictated by IGNERP standards. So after 120 kilowatt dynamic wireless charging system, we noticed that the numbers are getting closer to the limits. They're still further away from the limits, but they're getting closer. So when we go to 300 kilowatts, we were worried about maybe the leakage fields without any shielding. So we started looking at passive and active shielding, and we came up with some new ideas on the passive shielding that will actually reduce a lot of these fields. So something else we noticed while we were studying the shields too, some of the automotive companies actually, they stopped working on wireless charging, and there is a chance that they might have been because of the leakage fields. So I think with these shielding technologies, we can reduce the leakage fields, and maybe this might help some of these automotive companies to adopt wireless charging back again.
Okay, one last question. This comes from the HUA site. Would the dynamic vehicle assembly be compatible with the static ground assembly?
That's very important. Interoperability is really important, and that's what we want to do. At the end, for now, we're demonstrating. So if you look at our static system, we're looking at a polyphase system. And for the dynamic, we have a double D system and a rail system in the ground. So they have some compatibility, but they are not the exact same coils, because we're looking at interoperability of different coils. At the end, you have to have some kind of interoperability. Otherwise, if the vehicle, the WPT system works on the vehicle in static and then not dynamic and vice versa, I don't think it will work.
Thank you, Burak, for those wonderful, very quick answers. And we got through quite a few questions. Again, I want to thank from behalf of all the audience. We have 2,500 people registered, some of whom will be watching this after it's recorded because it's nighttime in China and parts of Asia. But thank you for a wonderful presentation and for answering all these questions. I'm going to hand this over now. Yeah, well, thank you, Burak, and I hope you can stay for the some of the papers that are going to be presented in the technical session. Otherwise, it's all recorded. So I'm going to hand this over to our session chair, Zichao, and Sung Young An to sort of guide us through the technical session. Thanks, everybody. I want to thank all the audience for being here.
Yeah. Hi, everyone. My name is Ji Chao Luo. I am a postdoc fellow in University of Toronto, and I am one of the chair of this technical section. Together with me, we have Sung Yang An, who is an associate professor in CCS Graduate School for Green Transportation, Korean Advanced Institute of Science and Technologies. So we are going to host these technical sections. So I will give a brief introduction about how we are going to run this technical section. So first of all, we are going to let all the presenters give 2 minutes summary presentations one by one. And after that, there will be a Q&A sections for all of the presenters. So both the presenters and the attendees can type in their question in the Q&A box in Zoom or Whova. And if they want to talk to the presenter in person, you can also raise your hand and we can allow you to talk. So right now I will share my screen. Just wait a second. So can everyone see my screen now?
Yes.
Yes. Okay. So yeah, we are going to start from the first paper in our technical section. And the paper title is Study on Soft Startup and Shutdown Methods for Wireless Power Transfer for the Charging of Electric Vehicles. And the presenter is Kelvin from Delft University of Technology. Yeah. So if you want to advance the slides, so please notice me. Yeah.
Yes. Okay. Yes. Thank you. Yes. Hello, everyone. Yes. Welcome to my pitch about the, as mentioned, about the study on soft startup and shutdown methods for wireless power transfer for the charging of electric vehicles. Can you proceed to the next slide? Yes. So wireless power transfer.
Sorry.
Okay, so wireless power transfer systems becoming more and more popular for EV charging, and especially imagine when we have this dynamic charging, then the car constantly needs to go from one charging pad to the other charging pad, which means that it constantly needs to start up and shut down again when it is moving. So it is very important to have a safe startup and shutdown due to the high circulating currents. Also because this is getting, because this process is getting more and more, when you have this startup and shutdown constantly, you also want to have this source switching to reduce the losses and have a higher efficiency. So we want to have a method that can preserve source switching and reduce the current amplitude at the start. So in this paper, we benchmarked 3 source startup methods and 2 shutdown methods for the SS compensation, and 3 source startup methods for the double-sided LCC, which are the for the series compensations, the phase shift control, frequency control, and dual control, and for the double-sided LCC, we have a combination of the phase shift control and frequency control at different frequencies. One of the main takeaways are that for the double-sided LC, you want to be below the resonance to be in the inductive region. And for the series compensation, you want to be above the resonance to be in the inductive region to secure this soft switching. And we saw that for the series compensation, the dual control would be able to maintain soft switching over the whole startup and shutdown process, and also reduce the current amplitude. And for the double-sided LC, we saw that when we start at 79 kilohertz with the frequency control, and also slowly increase the duty cycle again with the phase shift control, that would give the best result. However, this is there won't be soft switching in the startup transient, which brings me to my to my conclusion, is that that there's still a need to for soft switching at the startup transition for double-sided LC, but for a series compensation, should be able to do it with this dual control to secure the soft switching and also reduce the current amplitudes. Yes, this is the end of my pitch. Thank you for your attention, and if you have any questions, you can let me know in the Q&A box. Thank you.
Yeah, thank you. So we are going to move forward to the second paper. The paper title is 110 watt e-scooter wireless charging operating at 6.79 megahertz with ferrite shielding. And the presenter will be Christopher from Imperial College London. So yeah, please go ahead.
Sure. So yeah, hello, I'm Christopher Kwan from Imperial College London. I'm also part of Bumblebee Power, which is a spin-out company of Imperial focusing on high-frequency inductive power transfer. This paper showcases a 110 watt wireless charger that we have built for an e-scooter operating at 6.78 megahertz with ferrite shielding. In recent years, we have seen a huge increase in the popularity of micro e-mobility, such as e-bikes and e-scooters. Adding wireless charging to these types of vehicles can offer enormous benefits in terms of safety, convenience, and reliability in comparison with existing methods of either wired charging or battery swapping. In our system, we have attached the receiver unit to the bottom of an e-scooter. This unit consists of a 12 by 24 cm PCB coil, a voltage doubler full wave class D rectifier, and ferrite sheets that have been inserted between the receiver PCB and the scooter. The ferrite sheets act as a shield between the magnetic field and the solid aluminum alloy base of the scooter. On the transmit side, the ground pad consists of a 25 by 30 cm PCB coil and a push-pull class EF inverter with GAN devices. The DC to DC IPT system was operated at a power level of 110 watts to a test load with an efficiency between 69 to 75% efficiency. After integrating the off-the-shelf mains interface and the battery charger, the overall efficiency from mains to battery was around 51 to 56%. Our wireless charging system also exhibited good tolerance to misalignments, and this is an important feature, especially for electric scooter applications. So to summarize, we have successfully integrated a 110 watt wireless charging system into an e-scooter with an operating frequency of 6.78 megahertz, which is an ISM band. We have achieved a DC to DC IPT efficiency of between 69 to 75% with the use of ferrite shielding, PCB coils, and high frequency resonant power converters. Thank you all for watching.
Yeah, thank you. And then we are going to the next next paper, and the paper title is Z-class LCCP compensated IPT system with a reverse coupled compensation inductor. And the presenter will be Amar from Drax University. So yeah, please begin.
Thanks, Dr. for the introduction. Yeah, I'll be presenting an LCCP compensated IPT system with a reverse coupled compensation inductor. If you can go to the next slide, please. Thank you. So misalignment represents a pretty significant issue in vehicle wireless power transfer systems. And we're proposing a passive method to control the misalignment. In this case, we have an LCCP structure, and we use LF1 and L2 coupled together to improve misalignment performance. Our key results here on the left side, we can see that the blue line represents our output power with our system, and the red line represents the output power if the cross coupling was not engaged, and this is in the simulation. We see that misalignment tolerance is reduced by about 31% in the simulation and about 20% in the experiment. Under our method, we have our experimental setup. It consists of two coils. One large coil is the transmit coil, and the smaller coil on the top is the receive coil. The coils are designed to minimize the reduction in coupling within the coils, so it makes the job of this method easier. And then to conclude here, we list here our experimental results. We're able to transmit 3 kilowatts of power, and we achieve a peak efficiency of 95.8% and a minimum efficiency of 91.5%. Thanks for listening.
Okay, thank you. So we are going to move to the next paper. The paper title is, is output power control of an SSIPT system based on voltage and frequency tuning for EV charging. And the presenter is also Ahmed from Drexel University. Yeah, please.
Yes. Yeah, you can just go ahead to the next slide.
Okay.
Okay. Thank you. So here we also pay attention to misalignment performance, but we do so in a bit of a different way. We think of the approach from a control side instead of a passive coupling side. And our approach here is to use frequency detuning and voltage boosting as a hybrid approach to control the wireless power transfer system. And the goal is to maintain power, but in the peak power case, but also to control power. So the aim is to be able to achieve any power level to the load from 0 kilowatts to 3.3 kilowatts, which is what we tested here. And we want to be able to do so under any output load condition of the battery and under like misalignment. Lateral misalignment here. We test about 100 millimeters by 100 millimeters, and we are able to achieve power control throughout the entire range. Our key results here, I show 1 point in these slides because we're constrained by some space, but P1 is the well-aligned low battery voltage state. And we can see that the red line represents the power levels and the black line represents efficiency. And this is experimental results. So we can see that our efficiency is maintained throughout the majority of the power range, and the efficiency is maintained pretty high. On the rightmost side there, we have our ferrite, our coupler. And the transmit is the one on the left, the receive is the one on the right. Our method and approach here. So in this experiment, we use an SS compensation strategy, but our approach here is targeted towards multiple compensation strategies. And what's done is we generate these performance maps using an SS. We generate these performance maps. And the performance map basically represents every combination of frequency and voltage and the power that results from that combination. And the heat map in the back is the power, is the efficiency, and the crosshatched lines represents the area where ZVS is achieved. So you can see in this region, ZVS is achieved in the entire region. And each one of those lines represents every combination of frequency and voltage that can achieve this power level. Finally, we have our experimental results. We're able to achieve a peak efficiency here of 95.7% at 3.29 kilowatts. This is achieved in the P2 region, so the high battery voltage region. And we achieve about 93% efficiency with 100 millimeter by 100 millimeter misalignment. And we're able to control the system in that full range between 180 volts and 240 volts, which is supposed to model the average voltage fluctuation in the lithium-ion battery. Thank you.
Yeah, thank you. Yeah, thank you for your fruitful outcome sharing here. So we are going to move to the next paper. The paper title is the high, the paper title here is the high efficiency, there's some block on my screen, so I have to. Yeah, the paper title is a high efficiency. This is something wrong. So yeah, please just I will invite the presenter Wasuki Habesawa from the Panasonic Corporation in Japan. And yeah, you can just introduce your paper title, and also if you want to advance the slide, please let me know. Yeah, please go ahead.
Hello, my name is Habesawa from Panasonic. Today I will talk about wireless power transfer for waveways. Next page, please.
Okay.
Thank you. We are trying to apply wireless power transfer to underwater mobiles such as AUVs. Considering the battery capacity of AUVs and the ocean currents, we have decided on 3 requirements for wireless power supply in the sea. The first is high degree of freedom in position. The second is high efficiency, and the third is high power consumption. We built this wireless power transfer system to meet them. A power receiving coil is placed inside the 3 power transmitting coils with a diameter of 1 meter. The AUV is a metal pressure resistant container on which ferrite is pasted and the coil is bound. This is a cross section. The coils are arranged at the interval of 500 millimeter, and the coils are prototyped with a waterproof structure. The photo above shows the experiment. The power transmission coil was lifted and submerged in a tank filled with salt water. The transmission frequency was set to 2 kHz. The transmission power was set to 1 kilowatt, and the transmission efficiency was measured by changing the position of the power receiving coil. It was confirmed that wireless power transmission was performed with an efficiency of 86% to 87.5%, even if the position was changed inside the power transmission coil. The conclusion: we have been able to perform wireless power transfer with high efficiency and a high degree of position freedom using high input power. Looking at the power loss by simulation, it is found that the conductor loss accounts for the majority, and the seawater loss is large near the power receiving coil. In the future, we plan to conduct experiments such as charging in the actual sea area. That is all my presentation. Thank you for your attention.
Yeah, thank you. So we're going to move to the next paper. And this paper title is a 400-watt UAV/drone inductive charging system prototyped for overhead power transmission line patrol. And the presenter is Su Chi from Toshiba Corporation in Japan. So yeah, please begin your presentation.
Thank you, Dr. Lo. I would like to briefly introduce our joint work with Toshiba, Prodrone, and Tokyo Electric Company Holdings. Next slide, please. Our goal is something like that. In our observation, the conventional wireless charging for UAV or drones have charging power have 250 watt or less. Then takes a very long time to charge only the 50% of typical battery for a mid or large size drone. Our project's final goal is rapid wireless charging, which have the 750 or 1000 watt to reduce the charging time for large UAVs. I would like to introduce today as a tentative result, a 400 watt drone inductive charging system. Our method is to use the unique shape, the frustum shape wireless charging port installed, transmit coil and ferrite plates. Before actual wireless charging process, the drone comes just above this wireless charging port and coarsely aligns its direction and descends down to this wireless charging port. In this mechanism, receiver coil frames automatically aligns its direction and fits into the charging port. So the misalignment on the landing is negligible. And moreover, no heavy ferrite on drone is required, so the weight of receive pad is very lighter. We measured and tested our system, and measured coupling coefficient is as large as 0.552, and average power is 435 watt. And total efficiency come around the 75 to the 78% during the charging process. We also tested in the field of the sequential operation, landing, rapid wireless charging, taking off, and high precision photo shooting of the line, power line. This successful test shows the substantial potential of the proposed our system for opportunity charging for long range overhead power transmission line petrol. Thank you very much.
Yeah, thank you. So we're going to move to the next paper. And the paper title is Comparison of Lumped Primary Coil System with SAE J2-54 Secondary Coils for Dynamic Wireless Charging. And the presenter is Anna from University of Stuttgart, Germany. So yeah, please begin the presentation.
Yeah, thank you, Chin-Chao, for the introduction. You can already switch to the next slide.
Okay.
So in the SAJ 2954 standard, this is the standard for static wireless charging. There are two different coil designs proposed for each WPT class, for each power class, which you can see in the upper left picture. The circular coil and the double D coil. And the question we asked ourselves is which one would be more suitable if electric vehicles will be equipped with the secondary sites? Which one of the coil designs would be more suitable for dynamic wireless charging? And to answer this question, we constructed the coils according to the standard and proposed an air coil system corresponding to the circular and the double D coil as a primary coil path. In the lower left corner, you can see our approach. We have a measurement of the coupling factor map. That is where the secondary coil has just been shifted in X and Y axis, and also for different Z distances. And also we put several air coils at the primary path and measured the coupling factor path when the secondary coils moved along the path. In the upper left picture, you can see the main results. As you can see on the y-axis, there is the coupling factor K, and on the x-axis, you can see the position. So this is in the lower left, it's the right picture. And the main result is that for the double D coil system, the coupling factor appears to be more stable and also higher, which you can see on the blue line, because the changes in the coupling factor are only 14% in comparison to 72% for the circular coil. So the main result would be that the double D coil seems to be a little bit more suitable for the dynamic wireless charging scenario. But we also saw that the circular coil appears to be more stable when it comes for lateral tolerance. So yeah, that's the main result, and the geometry and all the data you can find in the paper. And I'm looking forward to your questions. Thank you very much.
Okay, thank you. So we're going to move to the next paper. And the paper title is Power Electronics Packaging for In-Road Wireless Charging Installation. And the presenter will be Alex from University of Warwick, UK. Yeah, Alex, please start your presentation.
Yeah, thank you. Thank you very much. We can move to the next slide.
Okay.
So what we were looking at in this paper was some questions we had on effectively what happens when we take our power electronics and we put it in the road. That's something that was very relevant to our keynote speech today for dynamic wireless charging. It's also something that's relevant for static wireless charging, because as we have more and more electric vehicle infrastructure, we don't want to have too much street clutter. So the potential for embedding our power electronics and coils all in the road keeps it nice and seamless from the viewpoint above. But the question we had was effectively, how hot does a wireless system get when we do embed it in the road? And what are the things that generally affect this? So we set about making a thermal model of a representative wireless system, including the surrounding ground materials. The ground materials were set according to the standards for embedding things in roadways in the UK. And we wanted to examine effectively a range of scenarios and design choices that we had available to us. The key results, we have a much improved understanding of likely temperatures within an in-road wireless charging installation, especially given that when we started this study, we couldn't find much in the literature on this side of things. So here is a study where we've looked at various different aspects. We've also looked at what different environmental conditions and design decisions have, what the effect of those is on the temperatures we see. To conclude, we've looked at effectively passive thermal management options, which we believe is possible with good design. We simulated a 10 kilowatt wireless charging system. The contribution of ground to heat transfer can be significant. So in this case, we had approximately 50% of the heat lost effectively vertically through the pad and 50% lost through the ground. So the ground was taking 50% of the heat power. The time constant in the system was very large, so that gives potential for duty cycle type operations. Obviously, that depends on where you install it. And really what we wanted to do with this paper is effectively give an insight for system designers of what to expect from the ground so that you could then consider that in a larger overall design study where you've got to look to trade off not just thermal effects, but also sealing, robustness and vibrations and the like. So we wanted to sort of give a feel for what you might expect. Thank you very much. Happy to answer any questions.
Yeah, thank you. Yeah, we're going to move to the next paper. The paper title is a Basic Evaluation of Electrical Characteristics of Fair Wireless and Capacitorless Coils by Road Embedment Experiment for Dynamic Wireless Charging. And the presenter will be Koki from Tokyo University of Science, Japan. Yeah, Koki, please go ahead.
Hello everyone, my name is Koki Hanama from Tokyo University of Science in Japan. Please next page.
Okay.
In this study, freightless and capacitorless coils were embedded in the road and their electrical characteristics were measured. Also, strength tests of pavement were conducted. In the previous study, coils were made of styrofoam called XPS, which had good electrical characteristics, but there were concerns about strength and durability. Therefore, in this study, we compared 2 coil types and 3 different materials and 4 different construction methods. As a result, we were able to clarify the change in electrical characteristics of freightless and capacitorless coils before and after embedment, which had not been discussed yet. And then thermocouple measurements showed pouring cement was able to reduce the temperature during the construction by almost 20 degrees more than the other construction methods. However, cement-based materials were found to have a more negative effect on electrical characteristics than asphalt mixtures. The results of the strength tests shows that XPS has lower durability and pavement strength than the resin coils, and it is not suitable for pavement structures. The ultimate goal of this study is to achieve a balance between electrical and mechanical characteristics. That's all. Thank you.
Yeah, thank you. So we're going to move to the next paper. The paper title is The Influence of Contamination Between Receiver Coil and Embedded Transmitter Coil for DWPT. The presenter will be Zhe Fang from the University of Tokyo, Japan. Yeah, please go ahead, Zhe Fang.
Okay. Thank you for your introduction. And my name is Zhe Feng, and I'm from the University of Tokyo, Japan. And this work is cooperated with Denso Corporation and Obayashi Corporation in Japan. Please go to the next page. Thank you. So the transmitter coil in the DWPT system is set in the public road, avoiding the collision with the vehicles, which is different from the coil placement is different from the static wireless power transfer system. And the contaminations from the image, that the contaminations are easy to enter between the coils. So this work is to evaluate the influence of the contamination existing in the between the coils. And coils are transmitter coils are abundant in our lab's experiment spot. And the circuit topology is SS type. And we use LCR meters to measure the change of the coil parameters. And about 1.5 kilowatts power transmission experiments has been operated to evaluate the influence of the contamination on DWPT system with event coils. And our key results is showing on the right of the top. And the blue marks represents there are no contaminations between coils. And the red marks are the represents the tap water, which is simulated the rainwater, and the blue mark is represents the seawater, which the seawater is content with marine salts melting in the tap water. And from the results, we can find that the remained rainwater and the seawater decrease the AC to AC efficiency in the DWPT system with the dependent coils. And also the remained waters change the resonance frequency for the DWPT system. And we also consider the air sand, which is commonly used in the road construction, but there is no concern about the air sand will affect our abandoned coil WPT system. So thank you for your listening. And if you have any questions, please tell me. Thank you.
Okay, thank you. So we are moved to our next paper. The paper title is Semi-Dynamic Wireless Power Charging System for Autonomous Electric Vehicle. And the presenter will be Gu Ho from Korea Advanced Institute of Science and Technology. So yeah, please go ahead.
Hello, can you hear?
Yes, yes.
Okay, so hello, I'm Gu Ho from KAIST. I'm going to present semi-dynamic wireless charging system for autonomous electric vehicle today. Next slide, please. I'll talk about the goal. So as you can see, our system is consists of two parts. One is the semi-dynamic wireless charging system, including long length of dynamic power line module and short length of static line module. And so the other is the pickup system inside and regulator inside the vehicle. I'll talk about the method. We carried out the magnetic field simulation, and we installed our system in KAIST. So this is the we installed 5 meter dynamic power line module and 1.5 meter short length of static line module. I'll talk about the key result. So this table shows the power efficient result of power efficiency and out power depending on the lateral deviation and length of power module. We obtained about 92% of maximum efficiency, and also we got 86 of average efficiency. The conclusionally, we presented the dynamic wire charging system, and also we verified our system through the simulation and the implemented test bed in KAIST. Thank you.
Yeah, thank you. So we are a little bit over time, but right now we are going to the Q&A section. So both me and Dr. An will going to ask the presenters question raised by all the attendees and presenters. So right now I will give the floor to Dr. An. So Dr. An, could you ask some question to the presenter?
Yeah, actually we have some questions in a Q&A room. So maybe I should read them. Maybe they can see that. Okay, the one actually there are 3 questions from Victor Chang. One is for the paper number 3. So are you here, Mr. Amr Mustafa?
Yep.
So he asked. The question is that can you explain a little bit more on how the coupling helps with the misalignment mitigation?
Okay, sure. So actually, this is actually a really good question, because it's not immediately apparent how LF1 will help. And actually, if you look at the theoretical analysis of the circuit, the coupling between LF1 and L2, there's no real power transferred. I mean, we don't have time to go into the deep theoretical analysis now, but what I can say is that there's no real power transferred between LF1 and L2. That's number one. And then number 2 is that actually LF1 is also coupled with L1 and L2, and the combination of the couplings result in LF1 to L2. That ratio controls the ratio of reactive power on the transmitting side. So what you have is the same amount of power. If you combine real plus reactive power on the transmitting side, it remains approximately constant. But if you look at the ratio of real to reactive power as the coupler is shifted, the real power becomes a larger percentage of the overall coupling. So you're actually playing with reactive to real power here and not really transferring power between LF1 and L2. I hope I answered that question for you.
Thank you very much.
Yep.
So, and the next question is for the paper number 4. So the author,
okay, that's also me.
I actually read the wrong name. Once again. So is there more larger and sorry.
I'm guessing
more
larger
IO coils. Yeah.
Okay. So
right.
So the size of the coils here is shown here. It's kind of small in this figure, but it's 450 millimeters by 450 millimeters on the transmitter side, and 250 by 250 on the receive side.
Yeah. Okay. Yes. Actually, he meant that how large your coil is. Yeah. Okay. Thank you very much. And another question for paper number 6. So maybe Mr. Obayashi, are you here? The question is, what effort engineering was done to increase the power levels?
Okay.
So can you answer for this?
Can I show up my slide showing the block diagram?
Okay, yeah, I can just stop sharing and then you can share your screen now.
Okay. Let me see. Yeah. Can I show the block diagram? Can you show?
Yes.
Actually, there are many aspects to select the components, especially we should select the light in weight for the components. maybe the main part is least wire selection. 10 ampere is relatively large, so we have to choose necessarily thick wire, and the compensation capacitor and the low pass filter using the capacitors and inductors, they are partly newly developed for the low loss. And as for rectifier, we use also the very low loss silicon diode. And of course, 85 kilohertz inverter is a main component to reduce the power consumption. It uses silicon carbide transistor. Thank you very much.
Thank you very much for the answer. Actually, yeah, there are no more questions from the audience, but actually I have one question for paper number 5, Mr. Hasaba here. Actually, you chose the frequency of 2 kilohertz, which is very low relatively compared with other applications. So can you explain why you chose the frequency of 2 kilohertz for wireless power transfer?
Okay. I choose 2 kilohertz because the C router has a hard conductivity, and the electromagnetic wave alternate much, and then I decide low frequency. Is it answer?
Okay. I didn't clearly hear your answer. So in the seawater, considering the loss.
Yes. Sir.
So you have actually, yeah, in another paper, I forgot which number, but actually, another paper also dealt with the wireless power transfer in a lossy material. So and actually, I also give you comments that actually, in my research group, we have published one paper for in transactions on EMC on the modeling of conductive material like seawater. So maybe you can also you can check the paper how the loss is affecting. But in that case, actually, of course, 2 kilo so frequency is very small loss. Yeah, as I understand. Thank you very much for the answer. So is there any other questions?
Yeah, actually, I can see some question from the HUFA platform. So the question is for the TS3/6. I think the presenter should be, let's see, should be Shuchi from the Toshiba Corporation. And the question is, what were the main parameters to consider to minimize losses of such small antennas?
Small?
Antennas.
Antennas? Okay. Let's see. I don't think it's not small, relatively large. You can maybe. Can I show up the photograph?
Yes, sure, please.
Let's see. Can you see the screen? Can you see?
Yes, I can see it. Yeah.
This is the size of the frustrum, and well, the transmit coil size is a little larger, a little smaller than this lower side base. So the almost, for example, let's say maybe a little less than 30 centimeters square. So I don't think it's not small for the transmission for the 400 watt transmitting power.
Yeah, so and there's another similar question. So one of the attendees is asking how we can actually increase this the efficiency of this system. So what do you think is the main parameters or main consideration that can increase the efficiency of this system?
Okay, yeah, that's the quite trade-off issue, because if the heavy component for low loss is used, if you use such a kind of low loss and heavy components, the drone should be heavy as well. So it will reduce the flight time of the drone. So it should be avoided. So we should have a kind of trade-off issue. So if you want to increase, for example, efficiency, system efficiency, we should maybe we should select the low loss but heavier components for example, the heat dissipation.
Okay.
Yeah. In our project, we have a trade-off. So we select the importance for the lightweight of the components instead of the efficiency. That's the rough question, rough answer. Thank you very much.
Yeah, thank you. So yeah, if there's any other question for all the presenters, please feel free to type it in the Q&A box. And if you want to ask in person, you can also raise your hand and we can allow you to talk. Is there any question for the presenter? Okay, so I think actually I have one question, so let me just check. Yeah, so I have one question for the presenter for the TS3/2. I think the presenter is Christopher. So I see you use the PCB printed circuit board as the coil in your system, right?
Yep, that's correct. Yeah.
Yeah, and then you operating it at 6.78 megahertz. So what's the AC resistance of this transmitter and receiver coil? So do you think the skin effect will influence the transmission efficiency of this system?
Yeah, so for this work, we didn't actually sort of properly sort of measure or simulate the resistance. What I can say is that on the receiver side, the PCB coil is quite close to those ferrite sheets. It's so we actually put those very thin ferrite sheets from Worth Electronic just sort of sandwiched between the scooter and the coil. Those turn out to be quite lossy actually. In the paper, I have this temperature plot which show that those actually on the receiver side, that became the hottest part at like 40-something degrees. So at least on the receiver side, it looks like the problem of the losses in the coil is not in the traces itself, but in the ferrites, in the losses in the ferrites.
Okay.
Yeah.
So is that there is a specific reason for operating this system at such high frequencies? So I mean, could you just bring it down to kilohertz or something so that the losses will also be lower?
Yeah, I guess kilohertz sort of systems tend to use heavier ferrites, like sort of ferrite bars or sort of ferrite structures. So for this application on an e-scooter, you kind of don't really want that. It's you want something very thin, very lightweight as well, and sort of less costly. So that's why we chose this sort of frequency, given the, yeah.
Okay, thank you so much. So Dr. N, do you have any questions collected from the attendees, or you have some question for the presenter?
Actually, I don't have any questions for it, so yeah.
Okay. Yeah. So and then yeah, I have another actually very interesting question for the paper. I think for the paper TS3/10 Koki. So in your paper, I see you are presenting ferroless and capacitorless coil. So could you please elaborate a bit on how this coil is constructed? So how can you achieve the ferroless and capacitorless coil in this such dynamic wireless charging application? Koki, are you?
Yes.
Yeah.
Sorry, I couldn't catch you. Please, one more.
What I'm asking is you are using the ferroless and capacitorless coils in your paper, right? So could you please explain how can you achieve ferroless and capacitorless coils in your system? Because we know that we need to use a capacitor to compensate for the inductance of the coils. And in your paper, you are using the capacitorless and ferroless coils. So could you please explain how do you build this coil? Actually?
Ferroless and capacitorless coil does not require a resonance capacitor, so it is low cost and there is no need to worry about insulation breakdown of the capacitor. In other words, it is advantage in terms of infrastructure.
Okay, so is this sensitive to the operating frequencies when you actually operate this ferroless and capacitorless coils? So how could you achieve the resonance when you operate this system?
Capacitorless coil resonance frequency is turns, number of turns adjust, increase and decrease. Yes.
Okay. Okay, thank you.
Thank you.
I have a very simple question for paper number 9. So you have considered the airflow in dynamic wireless charging. So what kind of software you have used for the calculation of this? Can you answer for this?
I think number 9 is Alex.
Yeah.
Yes, can you hear me okay? Yeah, so I have, we used COMSOL multiphysics, finite element modeling for the specific boundary condition on the airflow. We used a pre-published empirical correlation between airflow and effectively heat transfer coefficient from a surface.
Okay, thank you very much. I just have additional one very short question for the paper number 8. So so you have compared the coil structures for the WD and circulars, but have you considered, actually we have different types of charging coil types for different size and height or some types. So you have considered this type, but is your conclusion valid for other types of coil structure? Do you think like that?
So I guess you asked for my question, for my paper, I guess.
Yes, right.
Yes, that's a good question, actually. Obviously, because we just did the measurements for the course proposed in the paper, yeah, it will be a little bit yeah, off the table to say that this is general valid for all coil topologies. But in this case, because we also have different ground pad areas, we would say that for the distances that were used in the construction process for the secondary course, we would say that it's valid. But obviously, yes, it's it's much. It would be too much to just for one paper to examine all coil topologies, right?
Okay, thank you very much.
Yeah, due to the time constraint, we are going to ask the last question, which is from Seiho Kim. And the question is for Alex. Have you measured temperature within the actual system to compare with the simulation results?
You can hear me now?
Yes, yes. Please.
Thank you. Our aim for this particular paper was we have not validated the results with experimental measurements, but we aimed effectively through simulation to get an approximate picture of what the temperature distributions were and how these were affected by changes in various different parameters. And it's a lot easier to change things and view things in simulation than it is in an experiment. But yes, it would be something that would be quite nice to do when we're able to actually find a piece of road that we can install a wireless charging system like this one in.
Okay. Yeah, thank you. So due to the time constraints, so we have to close this technical section for today's now. So if you have any other question for the presenter, you can use the Hufa platform and you can just send a message to the presenter, and then you can also create a discussion room through the Hufa platform, and then you can discuss to whoever presenter you want. So thank you very much for all the presenters and keynote speakers from all over the world during the daytime or nighttime. So it will be very great to have all of you here to discuss about the stationary or dynamic wireless charging system. Yeah, well, I will give the floor to Dr. Alfredi.
Yes, I just want to remind everyone that the program starts tomorrow morning. We have 3 sessions tomorrow as well, including 3 wonderful keynote speeches and 3 technical sessions. So please check the Huva website. Also set the time there to your local time so you don't miss out on any of those great sessions coming up tomorrow. And I just want to thank everybody again for their attendance. And thanks Zichao and Sung Young and for running this very nice session. And thank you to all the technical presenters who were in this session and for contributing these papers. Again, thank you to our keynote speaker, Burak, who was here early in the session. Thank you all. I hope you have a great evening. I know you're all in different time zones. Some of you are just waking up. So hopefully we'll see most of you again in our next 3 sessions. Thank you.
Yeah,
very much.
Thank you. Good job.
Okay, I think we are the only ones left. Well, we have some attendees still here. Okay, so thanks again, Zichao and Sung Young. Sung Young, this must be morning.
Thank you. Yeah.
But Zichao is probably evening here in Canada, right?
Yes, it's evening. Yeah. Now we'll start the recording.
Yeah, well, look forward to seeing you tomorrow as well.
Yeah. Thank you, Dr. Ann, for
thank you, Dr. Ro. So yeah, it was very very stable session management. Yeah, thank you very much.
Wonderful. All right, everybody, take night.
Yeah, bye.
Okay,
Have a good day.